Okay. Hi. Hi, everyone. Let's start the last session of oral contributions. Now is the turn for Jan Schneider or Juan Sastre for the French. And he will speak about measuring temporal entanglement in experiments. So yeah, Jan, the floor is yours. Thank you.
Thank you very much. There was a little pointer here. Did we? Here it is. Thank you. Yes. Okay. Yes. So I want to present a work really quick that I did in collaboration with Aleix, Carlos, Stefano, and Luca here at the IFF or on the campus. Stefano is in Barcelona at the Supercomputing Center, and Carlos at the University in Barcelona. All right. So I want to talk about entanglement. I want to introduce a new concept that is temporal entanglement. And the old concept that I think everyone here in the audience is familiar with is spatial entanglement. I'm going to label it as spatial entanglement. Okay, so what is it? It's correlations between different regions in space. And I think I don't have to do a lot of advertisements for it, but it's very important in quantum phase transitions, for superconductivity, and for lots of things. It's the main building block of quantum information theory, and one of the things I want to highlight is that it can be a proxy for ergodicity in out of equilibrium dynamics. All right. So what is temporal entanglement? Is now just correlations across different regions in time. So what I mean by this precisely, I'll go into more detail in the following. But we want to emphasize that as such, it's very important for equilibration and thermalization. So, and this is what we want to study. This is the goal of this work, that we define temporal entanglement, and we're going to look at it and see what does it do, how does it behave, can we derive something of consequence in terms of thermalization and equilibration. All right, so let's have a look. A very slow introduction to my graphical notation. This is very smooth and very simple and very trivial. Expectation values are traces, and unity is always the trace of any density matrix. So even the time evolved density matrix, and I'm going to highlight it as a little quantum circuit like this. So you have the density matrix, the initial state in the center. Its bra and ket degrees of freedom are time evolved with u and u dagger respectively. The trace is now formed just by connecting the bra and its respective ket degree of freedom. And I'm just going to display this as a continuous sheet, so we don't care about how many qubits there are, but it's more or less continuous. In space, the horizontal direction and the vertical direction represents time. All right, and then the sheet is topologically a cylinder, which is just forming the trace of this initial state and the time evolution. So with this in mind, I'm showing you the expectation value of any operator. It's just going to be looking like this. It's the sheet, and somewhere at the bottom we place in the operator. All right, so now what is spatial entanglement? Spatial entanglement is characterized by a reduced density matrix, which is a partial trace. So we do not trace over all of the degrees of freedom of the bra and the ket, which is represented in a quantum circuit like this. So we just trace over half of them, for example. Not necessarily needs to be half, but yes. So in the following, everything is bipartite entanglement. I don't know if you were wondering that. But in the following, everything is bipartite. There's a single cut in the space, and this looks like this, right? So if I have my graphical notation, I cut my cylinder open, half of the system, for example, half of the system, and that is spatial entanglement. The degrees of freedom that live on this cut are the bra and ket of the time-evolved density matrix, and those are, that is what characterizes entanglement. All right, so what is temporal entanglement? It's just you cut 90 degrees to that. So you take your original original sheet of the partition function, and you cut it open into the time direction. And this is, of course, a very different object, right? So first of all, I have to plug in a little operator, because if I would cut this through all the way, it would trivially fall into the return to the trivial density matrix, which is just the trace over the time evolution of the initial state. But if I plug in a little operator here, the trace over the entire surface does not fall back to zero, to one, sorry, but to something interesting. All right, so that's a little remark. Second, I'm going to vary the length of the cut, and I'm going to vary the position of this operator, but not the cut. The cut's always in the center, and I'm going to vary the position of the operator. It not need to be here next to the cut. I'll just highlight it like this. And this object is intimately related to something that's in quantum field theory known as the influence functional, or in quantum information theory, a process tensor. Okay. Right, so now let's define entanglement. If we have this object, this is a transition matrix, we're going to define the trace of the transition matrix, just normally like this, and its alpha power. So we take the transition matrix, exponentiate it to the power of alpha, take the trace, which is just the normal procedure you would do with any Rayleigh entropy, and then you plug in this trace into the formula of the Rayleigh entropy, and those will be our generalized temporal entropies. Why generalized? Because the trace of the transition matrix can be a complex number. It not need to be a Hermitian, the operator, because it's not a transition, it's not a state, reduced state. It is a reduced transition matrix, and transitions can have complex eigenvalues and traces in particular. All right, so what do we propose? So we propose that you take a copy of your system and duplicate it twice. So if you know someone with an experiment, or you have an experiment yourself, please do the following procedure, because we are highly convinced that this will result in the measurement of actually this highly intricate complex number, and it goes a little bit like this. So if we just take the copy of twice the system, we're interested in alpha is equal to 2. So we just take the square of the transition matrix, which is just the transition matrix times transition matrix. In the end, we have to take the trace. So the trace of the square just looks like this. And this is topologically an avoided knot. I don't know if you see this, but it's an avoided crossing. So if you would put them on top of each other, you would go in sort of an 8, because you're connecting the second degrees of freedom of the first transition matrix with the first of the second transition matrix, and then you go over in a loop. And this looks in the sheet that I'm proposing just like this, where at some point we start with exactly this cut, and this cut needs to be traced over, and the trace over just results in this avoided crossing in the knot. And then we vary the length of the cut and the position of the operator. To be more precise, it looks a bit like this in an experiment. So suppose you have 2 replicas, and in total we have 4 coordinates, sort of. We have the left half of the system of the first replica, the right half of the first replica, the left half of the second replica, and the right half of the second replica. All right, and then you time evolve for capital T minus T, where capital T is the total length of this sheet. Just a normal system. You isolate them from each other. The 2 replicas do not interact with each other. You just time evolve, and then you perform the temporal cut, and the temporal cut, again, is measured by the trace of the 2 transition matrices, which topologically form this, avoided crossing. So you connect the second degrees of freedom of the second replica with the first of the first replica, and then This is just the matrix multiplication traced over, which just results in this type of connection between the two replicas. And this is very much measurable, so you can go into an experiment, make these, for example, in optical tweezers, make these interact while completely isolating them from this part, and then doing this flip, and we expect the following numerical results for this observable. For example, in the Ising model, we have a hopping into the XX direction, we have a magnetic field in the Z direction, and which is transverse, and a parallel field in the X direction. So why do we look at the parallel field as well? Because it breaks integrability. Integrability is one of those features in theoretical physics which imply necessarily that the system cannot thermalize, because there are too many degrees of freedom, and you can never start with some initial state and a Hamiltonian time evolution and finalize in a thermal ensemble. However, if you do not have integrability, you can thermalize. So this is what this little h here is for. If we set it not from 0, we break integrability and we get the following results, where I show you t versus j, the position of the operator and the length of the cut, in an integrable and in a non-integrable system, and they look very different. And this is just the Fourier transform of this object, respectively, in the integrable and non-integrable case, where where h is 0 or h is different from 0. And we see that in the integrable case, we gain a 0 mode, a gapless phase diagram, while in the non-integrable case, we have a gap in the observable, and this is what we believe happens always for all systems, that the temporal entanglement spectrum that comes out of this observable has a gap, and if it has a gap, oops, that's so fast. If it has a gap, it's integrable. If it does not have a gap, it's non-integrable, and we suggest that this can be measured in lots of systems. This is interesting because the setting this field to 0 is actually a fine-tuning problem. So if you can sort of check by the dynamics, if you actually have a non-integrable case by measuring how close are you to this 0 mode. All right, and with this, I'm already finished. So once more, really briefly, we think generalized temporal entanglements are represented by this complex sheet with an avoided crossing. These can be measured in experiments, for example, these optical traps, where you swap the respective replicas at some time, representing the beginning of the temporal cut. And the characterization of the system is then performed by measuring this two-point correlation function in this replicated system, which is, we hope, trivial. And the result are, for example, these figures. Thank you very much.
Okay. Questions, comments? Does anyone has any question?
Yeah. Thank you for the nice talk. Did you consider at some point not to have vertical cut, but let's say diagonal or whatever? When you have, let's say, entanglement, temporal, spatial entanglement, I don't know if it's possible even.
Hello? Ah, yes. Yes, I think people have already done it. There's a paper by colleagues in Pasadena. I think it includes John Preskill. They have looked at a diagonal cut, yes. But they are harder to predict. So part of the reason why we do this this cut here, actually I have this pointer, this beautiful pointer. This cut is because it represents in the conformal field theory that underlies the Ising model a very simple perturbation operator, and then we can have some sort of implicit, almost analytic idea of what's going on and why we actually expect the zero mode to appear. So the gapless phase in the integrable case and the destruction of the gapless phase in the non-integrable.
Okay, thank you.
Thanks for the talk. Maybe I missed a part, but when you have talked about the generalized entropy,
Yeah.
did you say that it can be complex, or
Yes.
can you? How is the physical interpretation of the imaginary part of the entropy satellite?
Well, so this is I don't know. It's a good question. So let's have a look. I don't know. I think I have some backup slides. Ah, yes. So this is the transition matrix, not partially traced over, right? So you have a left half and a right half of the system. So in analogy to the density matrix, which is not traced over anywhere, this is the transition matrix, not traced over anywhere. And then I partially trace over this object. And if you look at this, you see that only in particular cases, for example, the Ising model where you have reflection symmetry and the Hamiltonian is actually real valued. It's symmetric. It's not just Hermitian. The transition matrix falls into it has real values. Falls into the real numbers. But in general, this is certainly not the case because most of this blue mass here is coming from a unitary operator. Oh, sorry. It's coming from a unitary operator, and as such, it doesn't have real eigenvalues. It has complex eigenvalues. Does that make sense?
Well, I was asking about some physical interpretation when.
We are at the beginning of trying to dissect this observable. What does it do? How can we? Because at the end of the day, this sheet extended into infinity is what a thermal ensemble can look like. So it's made up all of these degrees of freedom along the vertical cut, but then we say at the end, but there is only one number, it's temperature, that represents all of these degrees of freedom. And how that happens is still a mystery. I mean, I think that's why we're so interested in it, because we actually have an idea of how can we compress these degrees of freedom into just one simple real number, which is temperature, for example. But yes, it's very complex. It has to do with the Jordan block structure of this, and I think on a intuitive level, we're not there yet.
Thanks.
Okay. With this, let's thank Jan again. Oh, there was another question. Sorry, I didn't show you.
I don't want to block you guys.
If there is no time, it's okay. And in particular, it's a question that I'm ashamed to ask because it means that I didn't get something important at the beginning of the talk. But I understand that you study temporal correlations, like and why are those correlations considered entanglement? Like I don't see the picture.
Yes, that's a very fair question.
Okay.
You sound like our reviewer.
Sorry.
Well, only in the parallel sense of these formulas. So there's a partial trace. So in the conformal field theory concept, time and space. Why care about the distinction? You have two directions. It's just okay. Then you can mix them with Minkowski, etc. Perspectives. But there, in principle, in 1 + 1 dimension, there are two directions in which you can principally cut. So everyone's cutting in one direction, we cut in the other. We use the same formulas that are in total analogy to normal entanglement. It's a partial. You plug in a partial trace over some matrix, and then that's why we call it entanglement. But we add the label of generalized.
Okay.
Okay, now yes, let's thank Jan again. And let's go to the next one. Okay, now it's the turn for Geoffrey Avellanet. I don't know if you also saw him in a PISC seminar like not a lot time ago. And he's gonna talk about absolute separability bounds for bipartite and multipartite systems. So yeah, the floor is yours.
Thank you very much for the introduction. As he said, I'm Jofre. I come from the Autonomous University of Barcelona, the Quantum Information Group, and I will present quite the same I already did in the seminar, but a bit shorter, which is based on the preprint that we published with Guillem, Jegos, and Anna last year. The first thing is that we focus on the separability problem. That is, you are given a state, it can be a pure state psi, and you want to know if it's separable, so if it can be written as the tensor product of the states in the local systems, or entangled, if it cannot be written in this form. And for mixed states, being separable translates into being expressible as a convex combination of the tensor product of the local density matrices. In general, this is a very hard problem. It has been proven to be NP hard numerically. So the set of separable and entangled states are far from being completely characterized. The most important criteria is the partial transposition criteria. So it's a necessary condition. Every separable state has positive partial transposition, but it's not a complete characterization because there exist some PPT states that are positive under this transformation, but that they are not separable. Other super well-known criteria, such as entanglement witnesses, that give us a hyperplane here, so we will know that everything here is entangled, but there are some entangled states about which we cannot say anything. Bell inequalities have a bit of the same problem, and only for pure states with the Schmidt decomposition, there's a complete characterization of these separable entangled states. I want to stress, though, that under local unitaries, the Schmidt decomposition remains more or less the same, since the Schmidt number doesn't change, and that its extension to mixed systems is far from trivial. So, in a specific, we work with only a subset of separable states that we would try to completely characterize, and those are the absolutely separable states. We refer to them as the ones that can be certified as separable just from their eigenvalues. So we suppress all the dependence on the eigenvectors of the system. This set is centered around the maximally mixed state, the normalized identity, and as you can see, it has a very interesting property that the state doesn't change under unitary transformations, global unitary transformations this time. So the set of absolutely separable states have the specific property that if the state is separable, then under the action of any possible unitary, global unitary, it remains separable. And similarly, we can define absolute PPT, for example, as the set of states that remain positive under partial transposition with the effect of any global unitary. This is especially important because in quantum computing, the gates are just unitary operations. So those are the states that will not get entangled under any possible action. In the literature, there are mainly two important results. The first certification is based on a ball, so the sum of the square of the eigenvalues being smaller or equal than a radius. And the complete characterization has only been achieved for the qubit QDIT case with this formula here. The most interesting approach, though, for me, is the conjecture of the set of absolute separability and absolute PPT being the same, but it has not been proven or disproven yet. So now, why is our approach different? We will not consider the typical identity tensor map applied on the state. We will use linear maps, but we will apply it to the whole state of the system. So if we can prove that our map takes any positive semi-definite trace one operator to a separable one, and that there exists an analytical inverse of the map, if we are given sigma, a state under scrutiny about which we want to know if it's separable, then the action of the inverse map on sigma returning to the set of states is a sufficient condition for separability. This is a very fancy way to say that if you are given a state sigma, you check if this has positive eigenvalues because it's hermiticity preserving, and then you certify separability. In specific, we use the simplest map, the reduction map, which is basically adding the identity to our state rho with a single parameter alpha. The inverse is also super easy to compute, and it has been proven that for these values of alpha, it fulfills these properties, so it's a sufficient condition. Our new approach is to realize that here we are basically subtracting a constant times the identity to our state. So it can be translated into conditions on the eigenvalues. The minimal eigenvalue of sigma for positive values of alpha has to be greater than this constant here, and for negative values of alpha, these two terms flip, so the maximal eigenvalue of sigma has to be smaller than this constant. Now we will compare it with the current literature, and I will plot it just for 3 eigenvalues, so it can be represented even though it's not a physical system, and in specific in barycentric coordinates, so it's 2D and easier to understand. The blue triangle or the blue simplex is the set of normalized states, so the 3 eigenvalues sum to 1, and we can see that the condition of the minimal eigenvalue being greater than a threshold gives us a concentric simplex but smaller. And the dimension of this simplex is given by the parameter alpha plus. With negative values of alpha, we get exactly the dual simplex up to a scaling factor. And as we can see, the two of them are incomparable. So there are some spectra that are detected with one criteria and some spectra that are detected with another one. So we went to and computed the convex hull of the two criteria, and this way we can get a much tighter approach to the set of absolute separability. And in specific, I think this is the nicest result, we have been able to prove the formula of this linear convex hull as depending only on the parameters alpha plus and alpha minus and the total dimension of the Hilbert space. Notice that here we have a dependence on more eigenvalues than just the minimal or the maximal, but the number is bounded and is smaller than half the eigenvalues of the system in all cases. Nevertheless, we also saw that the ball that I introduced earlier has some states in the region here that were not detected by the linear convex hull. Doing the convex hull of a simplex and a ball in arbitrary dimensions is harder, but it is still important because here we can see the region that we gain, some spectra that we also detect, and in this plot of the minimal eigenvalue of the density matrix as a function of the purity, we see that the new detected area is relevant. For that, we went to numerics and we present an SDP that's super simple. You are given a state sigma and you want to express it as a sum of one absolutely separable state that is detected through the linear map inverse and another one which is detected as a function of the ball. And as you can see, if you plot uniformly distributed spectra, you recover the very same figure that we were expecting from the convex hull. Finally, in the paper, we do an extension to multipartite systems of the type CD to the n, and we just needed to find the parameters alpha plus and alpha minus that we present here. And in the symmetric subspace or bosonic space, we do more or less the same. We find alpha minus and alpha plus for general n qubit systems symmetric. But if you want more details, I will leave it for later if you want to ask or check the paper. So with this, I think it's already enough. Just to remind you that we have presented absolute separability bounds that go beyond the literature. I introduced the conjecture before, and everything we have introduced supports the conjecture. And finally, we have provided a simple, fast, and efficient numerical tool to certify absolute separability. And just to finish, the main open questions on the topic are the validity of the conjecture and the non-linearity of the set, because it's known that absolute separability has an infinite number of extreme points. So you cannot draw a line, it's something curvy that still needs to be characterized. And that's everything I wanted to say. Thank you very much for your attention.
Okay, time for the questions. Anyone has any question?
Hi, Geoffrey. Thank you for your talk. Have you thought anything about absolute entanglement or something like that?
That's a very pertinent question. I don't know where you got it from. Absolute entanglement doesn't properly exist because you can always construct a unitary that takes any density matrix to a diagonal matrix in the computational basis. But we are working in extending these absolute separability concepts to the maximal entangleability that a given spectra can have. So for example, if your state is super, super mixed, it doesn't matter what you do to it, that it will never have Schmidt number greater than 3, or its negativity will never go past a certain threshold, or the von Neumann entropy of the purification will never go up to something. So yes, this is something that we are working on, and I also think that it's very interesting.
Okay, more questions or comments? Okay, if not, I think we will pass to the next one. Let's thank the speaker again. Okay, now is the turn for Carlos Sánchez Martínez from the UAM and IFIMAC, and he's going to talk about close encounters between periodic light and periodic arrays of quantum emitters. So yeah, whenever you want.
So hi everyone, thanks to the organizer for giving me the opportunity to show you my work here, and thanks you all for being here on Friday morning after the yesterday night social activity. So today I'm going to tell you about close encounters between periodic light and periodic array of quantum emitters, a work done with Frida Linda and my two PhD supervisors, Francisco José García Vidal and Johannes Feit. So first, let's present our two main characters, periodic light and periodic matter. When we talk about periodic light, we refer to the electromagnetic mode supported by metallic or dielectric nanoparticles, nanoholes, arranged in a periodic fashion, like for example, photonic or permanent crystal, but let's talk in general way about metasurfaces. So example of this periodic light are surface lattice resonance, bounded state in the continuum. Surface lattice resonance are collective modes that occur when the wavelength is comparable to the periodicity of the array. And bounded state in the continuum are ultra high quality factor modes that means that they have low losses. So this platform can be used as resonators, sensors, in topological photonic, optical neural network, etc., etc. So on the other hand, with periodic matter, we refer to neutral atoms arranged in two-dimensional arrays. Interesting feature of this system is their nonlinear behavior and the possibility to tunable entanglement. So this translates in many interesting applications like quantum simulation of a spin model in 1 and 2 dimensions, the promise of hybrid quantum computing architecture, and can be used as a potential building blocks for quantum repeaters. So our idea in this work is to put these two things together to get a hybrid system where to get the best of the two sides. So this would be our platform, a meta surface, and then an array of quantum emitters on top of it. And to get a real hybrid system, we need to get a strong coupling between the electromagnetic modes supported by the meta surface and the collective excitation of the array of of quantum emitters. So now you can understand the fancy name of close encounters. So for those who are not familiar with the concept of strong coupling, it is the regime of light-matter interaction where the coupling is bigger than the losses. In some sense, the light and matter degrees of freedom hybridize forming or behaving as a single entity. So now the goal of this work is to get a quantum theory for describing the strong coupling in this system, a thing that, as far as we know, has not done before. So to put a bit of context, a traditional platform for reaching a strong coupling is this Fabry-Perot cavity where we have a single emitter coupled to a single cavity mode. And this platform is described through a James Cumming Hamiltonian. Here is the emitter contribution, the single mode contribution, and the interaction term. And the losses are encoded in a Lindblad dissipator term in the master equation. So this model predicts that when the system reaches a strong coupling, the eigenstate of the system are not anymore the emitter and cavity energy, but two new hybrid states split in energy that we call polaritons. So can we use this prescription to understand our metasurface-like cavity? As you may guess, the answer is no. Our metasurface-like cavity is more like an nanophotonics cavity that are characterized by to be open cavities where the electromagnetic field is very confined to the surface with losses. So in some sense, the mode structure here is really complex and described through a continuum of modes. So maybe you don't see now the connection between these two systems, but you may think, we can think on repeating this periodically, and we have our metasurface-like cavity. So now that we are expert on this metasurface, we can see what is our model to describe the light-matter interaction here. So let's see it. First of all, let's be a bit clever and use that periodicity allows to reduce our full problem to a single unit cell. Bloch's theorem tells us that the electric field is the same between different unit cells up to a phase factor that contains the lattice vector and the in-plane momentum. So we can transform our full problem to a single unit cell with Bloch periodic boundary condition. And this allows us to write our full Hamiltonian in terms of a momentum resolved Hamiltonian that reads like that. And here, in the interaction term, we see the most important of the cornerstone quantity in our work, which is what we call reciprocal space or momentum resolved spectral density. And this quantity contains the full information about the light-matter interaction. Why? Here we see that we have the lattice sum of the imaginary part of the electromagnetic classical Green tensor, which is the solution of Maxwell equation. So this quantity tells us all about the electromagnetic field. And then we see that this quantity is projected on the emitter dipole orientation. So this tells us all about the light-matter coupling. So here, this is our, well, okay, before, this quantity can be extended to multiple emitters per unit cell. So this Hamiltonian is our quantum theory, but we have a problem here, that we have this continuum of mode that is not easy to deal with it. So we need practical description. We need to get rid of it. And for that, we are going to use the field mode quantization method developed in my group that yesterday my colleague and friend Maxine explained very well. So again, this quantization consists of mapping our original Hamiltonian to a quantum optic-like Hamiltonian where we are substituting the continuum of modes by a set of discrete modes that are coupled between them with losses to a Markovian path and, of course, coupled to the emitter. So why these two systems are, these two descriptions are equivalent? The trick is to mimic the original spectral density to the model spectral density that is associated to this quantum optic-like Hamiltonian. Look that the spectral density contains the parameters of the Hamiltonian. Then, by fitting this spectral density to the original one, we get the values of these parameters so in such a way that we are encoding all the information of the electromagnetic field in our Hamiltonian. So this works like that. Imagine that we have this spectral density, we fit it, and then we get the parameters. So this is our model. Now, let's see how it applies to two specific cases just to illustrate it. An array of metallic nanoparticles and an array of dielectric nanoparticles. Let's start with the array of metallic nanoparticles. We use this unit cell where the meter is in the z direction, oriented also in the z axis. So this is the spectral density that we obtain numerically, right? So in this path over the Brillouin zone. So the different features here are clear. This broad resonance is the localized surface plasmon resonance coming from the metallic nanoparticle, and the different sharp features are what we call surface lattice resonance, which is the hybridization of this plasmon and the diffraction order of the array. So now, once we have computed this numerically in our spectral density, is the time to fit it. So let's focus, for example, in the gamma point to illustrate how is the fit. This is the spectral density at that point. So we see that we need at least 4 modes to describe correctly the spectral density. So single mode approaches in this kind of system doesn't work. So then, if we want, we need to repeat this fitting procedure over all the region of interest. But yes, I told you that what we want is to get to show a strong coupling. But in this array of metallic nanoparticles, in this particular configuration, or just 1 emitter per unit cell, is not possible because the coupling strength is not enough. So let's switch to the electric nanoparticles and that support this bound state in the continuum, which I told you that are a high quality factor. For example, has a high quality factor. For example, let's be close to the gamma point. We see this narrow peak. So now, if we couple the meter here and diagonalize our system, we see a strong coupling. We see this nice radius splitting here in the crossing point and these two polaritons. And just to finish, I want to say that these two polaritons, because of the nonlinear behavior of the meter, are going to be interacting, and this is very promising for quantum technology because it can be used to generate a pair of entangled photons. So I just want to conclude saying that I have shown you a quantum description of a strong coupling between the collective excitation of periodic array of emitters and the block mode of metasurfaces, showing that we have access to polarity in our platform, which are promising for quantum technologies. And I want to stress here that this is a general formalism, because I have shown you I have illustrated with the sample of a spherical nanoparticle, but this is general for any nanophotonic structure, as long as you are able to compute numerically with console or any thematic formalism the green function of the electromagnetic field. So that is.
Okay, anyone has a question?
Thanks, Carlos, for the talk. I have 2 questions. The first one is, how do you define your quantum emitters? I mean, what do you mean by quantum emitters?
By quantum emitter, I mean any multi-level system.
Okay, but
it's not just a 2-level system. I just illustrated in the picture as a 2-level system because it's easier. But you can use to any multi-level system.
Okay. And the second one was that in your last part of the talk, when you talk about the BICs, the boundary state in the continuum, I mean, by definition, those modes are decoupled from the far field, no? Or the radiation. So how can you couple your emitters? Sorry.
The thing is that they are decoupled just in the gamma point. You see that this is black because but we are coupling it in very close to the gamma point in this region and in this region. Because of that, you see this white thing here. Because it cannot be coupled at the gamma point.
Yeah. Okay. That was my point. Okay. Thanks.
Any other question? If not, I think we will continue with the next one. Thank you very much again. Okay, it's the turn for Felipe Reibnitz-Willemann from the UA MIFIMAC, University of Montpellier, and Laboratory Charles Coulomb. Basically, he's going to talk about, can quantum-like beat classical uncertainty relations? We will know now. So.
Thank you for the introduction. Thanks for the organizers for the conference and everybody who are bearing with us until the very end. So yeah, as he said, I'm going to talk about, really ask this question, right? Can quantum light beat classical uncertainty relations? And at first, what I'm going to do, because I'm not really sure about how many of you are super familiar with quantum optics formalism, but okay, when we think about light, or more specifically quantum light, we can think of it as basically photons as particles, point particles coming at your detector. Let's say that here you have a detector. And you can characterize light, or one way to characterize light is by its statistics. So what I mean is that a coherent light, which is the most used one, or the one that we usually think of in the high intensity regime, just like a sine wave, for example. It's basically a bunch of photons coming at random to your detector, okay? And when you calculate the second order correlation function at zero delay, here G, which I think it appeared in other talks here in this conference, you get that it's equally to 1. It's exactly 1. And you have this effect that's called photon bunching, when you have this basically photons coming in bunches at your detector, such that the intensity fluctuations in your field gives you a correlation, the G2 at zero delay bigger than 1. And so this light, photon bunching light, is basically thermal light, for example, one of the many states that that has this photon bunching effect. And the photon anti-bunching effect, on the other hand, is when you have very well separated photons in time, and you have your correlation function being less than 1. Okay, so if we get this and put, instead of just the G, you plot your states as a distribution in photon number. So a coherent state would be a Poissonian distribution, okay, which resembles a Gaussian distribution, which is a very characteristic of random processes. A thermal state here would be a distribution that is called super Poissonian, in the sense that it has a variance bigger than the Poissonian, and it has a heavier tail, okay. And an anti-bunched state, or a Fock state, would be just a peak in your distribution. If you have an anti-bunched state, or if you have this G less than 1, you know for sure you have a non-classical state, okay. You are sure you have non-classicality or quantum effects here, for example, a single photon state or two photon state. If you have a G bigger than 1, you're not really sure. I mean, you can argue that a thermal state is the most classical state, right, because it's the light that comes from the sun. But there are other kinds of states. For example, Rodrigo told us about the squeeze states that they have actually hyper bunching effect, but still are very non-classical in the sense they have entanglement. Okay. And one of the questions we can ask, I don't know if I have it, no, is so how to characterize this non-classicality, right? Because the G can only get you so far, and it doesn't really tell you much about entanglement, for example. And another question we can ask is how this non-classicality scales with the intensity of your field, okay? So a little bit of motivation, let's say, to this work is these quantum optical effects in strong field physics. So exactly if you get your pulse or your field to be very strong, it has been a surge in activities in the last few years about effects in strong field phenomena, for example, harmonic generation, driven by a bright squeezed vacuum, or generation of optical Schrödinger cat states. You have a bunch of, for example, ionization, right? So above threshold ionization, to photon double ionization, whatever. You can have this type of phenomena, and it's nice to see when we have quantum effects in it, okay? And the question that I'm gonna ask exactly here is not about any of these phenomena specifically, it's more about the uncertainty in your field. So, for example, in two-photon processes, okay, how sure can you be that 2 photons in your field are being absorbed in a very short time while maintaining energy resolution, for example? Okay, so we want specifically to study the spectral and temporal properties of these multi-photon processes, okay? The baseline for our analysis here is gonna be a time bandwidth product or time bandwidth theorem that is true for every kind of wave, could be even a sound wave or ocean wave, if you want, that limits how localized a pulse or any wave can be in time and in frequency, okay? So if you want your pulse to have to be a good resolution in frequency and it still be short in time, you cannot do that. So if you make a pulse shorter, you're gonna lose some resolution in frequency, okay? So it constrains a simultaneous resolution, both time and frequency, of course. And this happens because these two variables here, the time and the frequency of the field is not really time. Here is not really the general evolution time, is really where you measure the field. They are Fourier transform pairs, okay? So you have this limitation. Another thing that we're gonna look at, as I mentioned before, is the mean square delay. So here, you calculate the mean square delay as with also the G2 function, but instead of normalized to the coherence, is normalized to in time. You can think of it as if you have your field here, okay, which is composed of a lot of photons. This function here tells you the probability of you having a photon at time t and another at time t plus tau. And then, if you go back to the picture that we have just a bunch of photons coming out your detector, this mean square delay would be just the mean, or like if you sum all of the little delays in every photon in your field, okay, and then you normalize to the number of pairs, just an average over the square of the delays, you would get exactly that, okay. And, well, no. For a coherent field and for any classical field, what you get is that the mean square delay is exactly 2 times the time variance, okay? And then if we plug this into the time bandwidth product, we can get, for example, a delay frequency uncertainty relation that tells you how short can be your delay between photons in your field constrained by the bandwidth. So we find this limitation in classical and coherent fields that you cannot be exactly sure that 2 photons are being absorbed at the same time or in a short delay while maintaining good energy resolution. And then we ask ourselves, how about non-classical states, okay? And so I'm gonna go again to the squeeze vacuum example, that one way to generate a squeeze state of light is with spontaneous parametric Down conversion, right? Where 1 photon of your pump field interacts with a nonlinear crystal, generating a signal and an idler. They are entangled in frequency / time, okay? You get that? And mathematically, we can describe this state as squeezing in one of the quadratures, right? Why we care about this is because in recent years, there has been a very great experimental realization of having bright squeezed vacuums. So have a very non-classical state that is also macroscopic. And this basically kick-started all these other works that I've mentioned before. If we calculate this delay frequency uncertainty relation for the bright squeeze vacuum, you would get a plot like this. So here's exactly the uncertainty relation over the entanglement time, which is basically how separated in time each pair of photons in your field is, and the mean number of photons on the intensity. And you can see here that the blue part of the plot is anywhere that we have an advantage, so actually below the classical value. So we have an advantage, a quantum advantage, let's say. But it's a very small part of your plot, let's say. So it's very constrained to the low intensity regime. Actually, if you plot here the gradient descent path in this plot, you get something like that. Okay, so here at the very low intensities, you basically just have the vacuum plus the 2 photon perturbation, and then you can have down to 0.5, which is actually the least you can have in any type of state like this. And you quickly lose this advantage, right? So you go back to the classical value at around mean number of photons equals to 1, so it's actually not that good. Basically is where all the coherent pairs in your field take over, and then you lose this coherence, you lose the effects. And so now one of the questions that we can ask is, so is 0.5 actually the general limit? So it's not possible to construct any state that is better than 0.5, and also, how much better can we do? Oh, sorry. And how does this scale in general with the intensity? Because here, of course, it scales inversely with the intensity, but how is this always true? Okay. So to answer that, we're going to look at, go back to the photon number states, let's say, which are not Fock states. Similar, but photon number states is more general in the sense that it can be entangled. Okay. And what we get for Fock states, actually separable states, is that our relation for every any Fock state, nth Fock state, is going to be exactly 1. So we don't have an advantage actually, although it's still a non-classical state, right? We don't have an advantage. So actually, for these types of states, the origin of any advantage here is going to come from entanglement. So there is a little bit of a technical detail. I'm not sure it's super important, but it's basically a way with this uncertainty Hamiltonian method, you can calculate minimum uncertainty states for any 2 observables. Okay. If we do that for a general photon number state, and then we do a nonlinear optimization routine in these parameters here, basically finding the minimum uncertainty state for any alpha, which would be any state at all, we can get something like this. So this is the uncertainty minimum, okay, that we get from this optimization routine against the number of modes that we include per photon. Of course, this is a numerical method, so we cannot include every photon. Sorry. Well, every photon also no, but every mode. So we have to truncate our expansion at some point, and we can see that this minimum uncertainty is saturating to some values here that depends on the number of photons that you include. For the 2 photons, it's 0.5, as we had before for the squeeze vacuum. But if we have 3 photons, it's not a half anymore, it's 2/3, and so on. So we get something like this. The limit that we get for any photon number state depends on n, and it goes 1 minus 1 over n. And this is actually exactly what you get from a maximally entangled Gaussian state. Okay, I cannot prove it analytically. It's quite hard, I would say. It's not at all trivial, but numerically, and also if we plot the density, we see that it gets very similar to a Gaussian density. And in the limit that you include every mode in your expansion, you would expect to get exactly a maximally entangled Gaussian. Okay. So this is the limit now that we find for a photon number state. What we're going to do then to study how, in general, this how low can be this uncertainty in general, we're going to do an expansion in photon number states, right? So if you do an expansion in photon number states, we get that the total delay of your field is going to be an expansion in n, so n is the number of photons, and then for every n or for every photon number state, you get some delay, and then you do basically a weighted average, right, to get your delay. The same with the bandwidth, but the bandwidth is a 1 photon observable, so the weight is just n, whereas for the delay, it's a 2 photon observable, so we get this delay that goes more or less n to the square. So it's, yeah, the weights are the number of pairs, and the weights for the bandwidth is just the number of photons. And then P is the photon number distribution that I showed before, okay? Doing this, and then doing a Cauchy-Schwarz inequality here, the minimum that you could have in general for any state is exactly this bound here that you can see only depends on the statistics of your field. Because here, we also assume that we have at every photon number subspace, we have the minimum that we found before, okay? So if we include that, if we take that, in the end we have this bound, okay? And then, okay, so we have this bound. It's not so pretty of an equation, I have to say. It has some square roots here, which are not easy to treat because fractional moments of distributions are not super well defined. But we can do some examples, for example, with thermal light that was seen before, or not thermal light, okay? It's a thermal light distribution, but it's not thermal light, not at all thermal. This state here, because of course you have entanglement and thermal light in general doesn't have it, not at all, but anyway, is the distribution of a thermal state. And you can see that I actually am below the 1 minus 1 over n limit that I had before. So for this thermal superposition, let's say, that has this limit at every photon number state, you get an advantage, and even at high intensities, you have an advantage. So if you take this photon number to be infinity, in the end you get exactly 9 pi over 32, which is 0.88, which is below 1, of course. And so it's a bright state with a better resolution. And even I didn't include here because the recent result, you can prove that this goes, in some cases, this uncertainty here goes inversely with the G2 function that I showed before. So if you have a hyperbunched state that G could be, I don't know, let's say 1,000, this uncertainty relation can actually go to 0, which is very remarkable. You can have perfect resolution, let's say, both in the delay and in frequency. And this comes from the fact that exactly there is this asymmetry in the weights. So if I have a distribution with large contributions in n very large, you see that this here grows square to the square of n, and this only with n. So if we have something like this that I showed before, so it's scaling in n of the delay like this, and the bandwidth like this, we can actually have an advantage because of this asymmetry. It's not obvious, but anyway, it's an interesting effect. And actually, if you then, on the other hand, you don't include entanglement at all. So if you assume that in every photon number subspace you have just one, you can actually still have an advantage. Okay, that's it.
I don't know if anyone has a very quick question because we have run out of time for this talk. Okay, so let's thank the speaker again and let's go to the next one. Okay, now it is the turn of Andrés Agustí Casado from the UAM as well. And he's going to talk about reinforcement learning for entanglement distribution in quantum networks. So let's see what.
Thank you. Thank you for the introduction. Well, I was told that I was going to be the last speaker of the conference. So I prepared a new slide deck that has no equations whatsoever, okay? It's only pretty pictures and text. You don't even need to read the text because I'm going to read it for you. So just enjoy. So yes, I'm Andrés Agustí, as you mentioned. These are my collaborators. Some are in UAM and others are in Politécnica de Madrid, okay? And well, these are my sponsors. Now we are going to, well, as Laura mentioned in the first talk, one quantum technology that we are not really used to seeing in this conference, but is also a quantum technology, is quantum communication, right? It's the application of quantum mechanics to cryptography, for instance. No? And one of the most known examples of quantum communications is quantum key distribution, and in this case, BB84, right? We all know this protocol that uses Alice is able to produce some qubits, some flying qubits that can be photons in some polarization bases, on 2 different polarization bases. And then Bob, by choosing randomly the basis in which to measure these states, they are going to, in the end, after lots of classical processing, they are going to be able to produce secure cryptographic key, okay, in a way that is impossible, given to the laws of physics, to crack, right? So the thing is that when you are trying to do QKD, for instance, there are other applications, but I'm going to focus on QKD. One very common question is how to increase the range of QKD, okay? And then the dissipation in telecommunication fibers becomes a problem. And well, one of the possible solutions, having the previous speaker right before me is very convenient. One of the possible solutions is to increase the signal strength, right? But the thing is that runs into some problems, because at the end, you can think that there are many ways to look at this, but you can always think that quantum mechanics is about nearly isolated systems. And in order to increase the signal, you'd have to put a lot of energy on a single place, okay? Okay. And if you put a lot of energy on a single place, it's difficult to keep it there, okay? So one possible alternative to this problem is to use quantum repeaters, okay? So for that, I'm going to introduce a new operation, entanglement swapping, okay? And the thing of entanglement swapping is that it allows for 3 parties, okay? The source, the repeater, and the destination. It allows for the source and the destination to share entanglement, even if they are not able to produce it between themselves, but only with the repeater, okay? The repeater has 2 qubits. This is very common notation for everyone here. This is just a quantum circuit, okay? So you're going to have this, the source is going to have a qubit, the quantum repeater has 2 qubits, and the destination has another qubit. And then somehow, because using this telecommunications fiber that I mentioned, you are able to produce an initial state that is entangled between the source and the repeater, and the other qubit of the repeater and the destination, okay? But you are not able to produce the final state. You are not able to produce an entangled pair between the source and destination. But you are able to, the repeater is supposed to be a small system in somewhere in space, so you are able to do a CNOT, okay? And then, well, this is half a Bell basis measurement, okay? This is a Bell measurement. And if the repeater communicates the results of the measurement to the source and the destination, then the source and the destination can end up in the entangled state that you began with, okay? The important thing about this operation, entanglement swapping, is that it allows for the creation of repeaters in the sense that the quantum repeater needs not to be trusted, okay? You could try to do quantum key distribution here and quantum distribution here, and then use the key of one of the connections to make key for the other connection, but you have to trust this node. In this case, the node might not cooperate with you, but if the node does entanglement swapping, you are secure in the quantum sense, okay? This is the important piece of information. I'm going to be doing a lot of entanglement swapping, so I need shorter notation for this. I'm going to write lots of graphs, okay? Imagine now the source is this green circle. I'm going to call her Alice often, and she has a qubit. So this is going to be, or a quantum memory. This is going to be the blue circle. Then she has this telecommunications fiber that goes to the repeater, who is often going to be Charlie, okay? Charlie has 2 memories, and then Bob is the same as Alice, but at the end, okay? And then the process is very simple. You produce entanglement within the fiber, okay? So you have 2 Bell pairs here, and then at the end, you have the swap consuming these Bell pairs and moving them to a different location in the graph, okay? So To be even more schematic, I'm going to forget about the stations or repeaters, and I'm going to put just the memories. Okay, so this is the memory of Alice. This is the first memory of the repeater, the second memory of the repeater, and so on. And then you know that two memories are on the same station if they have a solid edge. They are on different stations if they have a dashed edge. Okay, and then this is the process of entanglement swapping. Okay, very simple. Now the thing is, I'm going to be doing lots of them, okay? So you're going to have longer chains, and in general, you're going to have graphs. And the thing is that we need to account for realistic models. Anything can go wrong, okay? How do we capture in this very simple toy model the fact that entanglement generation may fail, entanglement swapping may fail, and quantum memories may decohere? Well, we can just put numbers on the graph, okay? We can decorate the graphs with numbers, and then what we mean with this one is that the probability of successful entanglement generation is 1, so this is the ideal case. The probability of doing a swap in this station is 1, and the entanglement contained in this bell pair is 1. Then the memories are going to reduce this entanglement over time, okay? So this is a very simple model that machine learning is going to be able to play with, okay? So that's the point. And we are going, the way to formulate this problem is that we are going to look for a policy. We're going to look for a function that takes the graph and returns a set of actions on that graph, or a probability of taking actions in that graph. And you can probably imagine that the optimal policy goes as follows. If the network is empty, then use all the fiber connections to generate the bell pairs, then do the swap, and that's it, okay? We call this policy greedy because it's doing everything it can at every moment, okay? And it's going to be the baseline we are going to compare reinforcement learning against. We are not the first to do this. There are other papers that do similar approaches, but we are going to extend those approaches to heterogeneous networks, beyond the chain network, and model-free, in the sense that the model does not need to know the specific parameters of the environment, of the graph, okay? And then, this is a lot of text, but just listen to me. The policy is going to be a neural network, okay? As I said, it's going to take as input the adjacency matrix of the graph, and is going to do some linear algebra and non-linearities as any neural network, outputs a probability distribution of taking actions, and we are going to sample an action from there, okay? Repeat this until you succeed entangling Alice and Bob, or until you run out of time steps, okay? Then you can use the algorithm called reinforce to update the weights of the neural networks to make the successful entanglement distribution likely, okay? So you're going to change the network on purpose to make success likely, or to make the reward go high. And then you can repeat this until convergence, until you improve the policy so much that you get to the optimal policy, okay? So now, results. First, a consistency test. We are going to train on a perfect chain, and then we know that the time steps that you need to entangle the end nodes is 2, okay? Because you only need to generate on every fiber and then do every swap. Then the reinforcement learning algorithm learns to do this. What is more interesting is to put a graph that is not a change and that is not perfect, okay? So here the generation can go wrong sometimes, and the graph is not a simple chain. Then we see that obviously doing everything you can at every moment over an edge that connects Alice and Bob, a path that connects Alice and Bob has this performance, okay? So it manages to entangle in these time steps, and then reinforce is better, okay? And the thing is that now we want to study networks that have worse parameters. These are worse parameters because we are making the entanglement swapping stochastic. In the previous slide, I was making the generation stochastic. Apparently, this is way more important, and this goes wrong very quickly. But it's because of the reinforcement learning algorithm that we are using, and we want to study larger graphs, okay? And I think this is all. These are my conclusions. We are successfully training reinforcement learning models that improve, that have policies that have better performance than human design policies. And there are other future directions, but are running low on time. So thank you very much.
Okay, does anyone has any question? In particular, I have one. Related when you go to more complex graphs, non-trivial graphs, what would you say? Okay, obviously you talking about non-trivial graphs. There are a lot, infinite ways of complicating it and everything. But I was just curious. Maybe it's a stupid question, but what would you say is the feature that breaks down everything more quickly, or that provokes more time steps? Or
I think having lots of different, I don't know if this microphone is low for me. Well, I'm not going to move this. I think the most complicated feature is, oh wow, science. The most complicated feature is when you have lots of different paths that connect Alice and Bob, and those paths have intersections between each other. If they are parallel, you just use them in parallel, and that's simple. But if you have to think, okay, what is the path that I need to use now for the particular state that I'm in, that's the tricky part.
okay, thank you. Any other?
Hi. So my question was is about more complex networks, and it's when there are multiple paths available, should you use some kind of routing algorithm or try just every path for the sake of comparing the results?
The benchmark that we use, greedy, doing everything you can all the time, it uses a routing algorithm in the sense that it looks for the shortest path and then tries to do everything on that path. The thing is that in that case you are not using the network's features, so you are expected to have a low performance. In that sense, you need to. Entanglement is a resource that has no clear direction. It's like symmetric and it's all over the place. It's non-local, right? So you need to use the full graph, and you need to let the model play with all the possible connections.
Okay, thanks.
Okay. Any?
So you have introduced imperfections in terms of noise, but have you thought about, or maybe have you tried or thought about trying introducing some kind of degradation of the entanglement due to the lifetime of the memories?
Yeah, that's how the memories go into play. For any time step, the quality of the bell pairs reduces over time.
Okay.
So, and when they go to a threshold that is too low for the application that we are thinking about, we discard that connection and it disappears from the graph.
All right. Thanks.
So can you go to the slide that show you like the reinforced learning do better than the greedy? Yeah. So in this case, which is the policy that the reinforced follows, or you don't know?
Well, this goes into the subject of machine learning interpretability, which is a complicated, a subject that is a bit foreign to me, and that it has a lot of open questions right now. But sometimes we have some insight on the policies that the machine learning model is producing. Like if you have a chain that has a very low probability of success, has a very poor swap capabilities, and has memories that have a lot of decoherence, then you are going to have to alternate doing swaps, but at the same time, if you alternate doing swaps, you take too long for the memories.
But it is possible in a particular case to find out or not? Like the concrete policy or not? I'm just asking.
Sometimes, like if you train on the perfect chain, on the perfect graph, you know what the optimal policy is, and you know that the reinforcement learning algorithm is going to go there. But in every other scenario, you only know that it's doing well, but you don't know if that policy is optimal because you might be in a
No,
local
not knowing that is optimal, but knowing which steps this policy follows in this particular case.
No, okay. In that case, the policy is just a table of given this state, these are the probabilities of taking actions. You can inspect that table if you want.
Okay.
Like
Okay.
I
That's
can
what
I can give it
I
to you
have to know.
if you want.
Okay.
Yeah.
Perfect. Thank you.
Let's thank the speaker. Ah, okay, very good. Very.
Do you know about the error threshold, that when it's total break or when it's...
There are some cases. No, for now, all I know is that this is my algorithm, the one that is running into trouble. But maybe if I use a different reinforcement learning algorithm, it is going to have a better performance.
No, I mean, you are playing with the error probability, right? And then do you play like when the probability is like really low, and then what threshold that it will like totally...
In principle, for any probability of error, there is some chance. Well, if the probability of entanglement generation somewhere is 0, then you are not going to generate entanglement, okay? But as long as every probability is bigger than 0, there is some probability of entangling Alice and Bob. So it might be very low. That's the problem.
Let's thank the speaker again.